Okay, so hopefully this would be our last part of our discussion on convolutional neural network, right? We'll not be discussing whole of it today, but we'll try to cover some initial parts so that once we meet in the next week, we have the required pre, you can say pre-knowledge for the advanced topics, right? So we have already seen an overview of AlexNet. We have seen transfer learning in two different frameworks, feature extraction and fine tuning, right? So basically what now we'll be looking at is regularization techniques, right? So I'll just tell you today what are those, and maybe we don't discuss this because this will require some derivation. So maybe even if we have to see, so we can see the subsequent regularization techniques, right? So maybe L1, L2, and batch normalization, this will be looking at in the next week, okay? So what are regularization techniques? In simple one-liner, regularization techniques are aimed at reducing or avoiding overfitting, right? From your knowledge of machine learning, I expect you have idea of what is overfitting, but just for completeness, I'll recall it, right? Suppose you have these points in orange on which you want to fit a model, right? So if I fit a straight line on this data, then you see my model is too simple, means it is not able to capture the whole information in this or the distribution in this data. So this is actually underfitting, where my model is too simple. If you see the third one, I'm trying to very precisely fit a model on this data, right? I'm trying to follow almost every single point. So this is called overfitting because here my model is very complex. When I say model, you will have an equation for this, right? So if it's a straight line, you have maybe something like 2x plus 4 is y, something like this, which is a first degree equation. As your polynomial becomes more complex, maybe you will have something like x4 plus 3x cubed plus 2x squared plus 6x plus 4. So the degree of this polynomial is 4. So as this degree increases, your model becomes more and more complex, right? Which is actually overfitting. And maybe we say, okay, this is an a visually it looks an acceptable solution where neither my model is too simple nor too complex. Okay. So this is just, you can say, an intuitive way of saying what is overfitting. But when you are doing an experiment, how do you know that your model has started to suffer from overfitting? So numerically or empirically, how you can do that? That you see an evidence of overfitting is the difference of performance that you get on training data or test data, or you can call it validation data, right? So as you increase the complexity of the model, what we expect the error to reduce, right? So as you are making your model more and more complex, right, your error is reducing both on the training and the test sets, right? But it is very much possible that you end up in a situation where after a certain point, the error on the training set is still going down, but error on the unseen test has started to go up. So this is an indication that you should have actually stopped here, and this should have been the optimal model complexity, because if you make your model more complex, you are actually suffering from overfitting, right? So again, coming back to regularization technique, so formally stating, we can say that regularization technique will make modifications to the learning algorithm so that it generalizes better. When we say generalizing, it means it is able to maintain its performance on unseen data, right? If your model is too much tuned to a particular data set, it is like learning by heart. It has a very good performance on training set, but a poor performance on the test set or the unseen data, right? Okay, so how actually we achieve this regularization, right? What we do is we actually discourage the complexity of the model by penalizing the loss function. It means that when we are doing training, we will make an attempt to make our model as simple as possible, right? So this is the key idea, that we are discouraging a complex model. Now, of course, since we are studying neural networks, so we'll see it from the perspective of neural networks. But before that, just for an intuitive discussion, maybe we can discuss this from the perspective of regression, where we are trying to fit a model on data, right? So it is only for intuitive discussion, right? Later, some of the things I will tell you are not exactly in the way they happen, but this is just for developing an intuitive understanding. Later, we'll be shifting to neural networks, right? So you see, in the regression, we have to fit a model on these points, right? And you already know that if this y is your ground truth and this f is basically what is predicted by the model, and this model is actually represented by an equation, right? So these theta which you see here, they are parameters. You can call them w or theta or anything. So you see, if your model is very complex, you have here a fourth degree polynomial, right? If you have a straight line, you will have maybe just these two terms. If you have a quadratic model, maybe you will have only the first three terms, right? So basically, the, the higher the degree of the polynomial, the more complex the model would be, right? Okay, now just imagine that somehow we penalize these weights theta 3 and theta 4, right? We make them very small, so small that they are close to zero, right? So it means that when they are close to zero, so actually you are suppressing these terms from this model. And when you suppress these terms, you actually get a quadratic model, right? So by suppressing these weights associated with these terms, you are actually making your model simple, right? So this is the key idea or hypothesis of regularization, that smaller weights generate simpler models, right? And once you have a simple model, we have already seen that it will help us avoid overfitting. Now let's see a bit more formally, that you see this was your original loss function, where you are computing the difference between the ground truth and the predicted value. Okay, so this was your original loss function, where this is actually computed by the model. Okay, now in the original loss function, you can add another term which is called the regularization term. The lambda you see here is a regularization parameter. I'll come back to that later. But you see, what is this term? You are actually adding all the weights or parameters, right? So when you are training the model, your objective is to reduce the loss. And when you are reducing the loss, you are not only reducing the first term, but also the second term. And in an attempt, you will be reducing the values of theta, and some of the theta values may end up close to zero, which is like suppressing them, right? And of course, this lambda is must be carefully chosen. If lambda is zero, then of course this term becomes zero, and you get back to the original loss function without regularization, right? If lambda is very large, so it means in the two terms, you have a very high weight on the second term. So when you are reducing the loss, many parameters or many thetas here will become close to zero, and maybe your model has the risk of suffering from underfitting, right? So that's why lambda is a parameter that should be carefully chosen. But again, no general guideline for this. Have to do it experimentally with hit and try, right? Now let's map all of this discussion to neural network, because that was just for understanding purposes. Actually, we have to do it from the perspective of a neural network. So from the perspective of a neural network, this illustration can represent the case of overfitting, where you see you have a very complex decision boundary, which is like giving you 100% on the training data, right? All the training data is perfectly classified. On one side of decision boundary, you have one class, and on the other side, you have the red class. But you see the decision boundary is very, very complex. You can already guess that ideally maybe it should have been something like this, a quadratic function. On the other hand, in case of you can say, if we introduce regularization with a very high regularization parameter, so what will actually happen? Many of the weights in the weight matrix, they will be close to zero. And when you say weight is zero, so it means you are actually eliminating those particular neurons from the network, right? For example, if the weights coming to this neuron are zero, so effectively this neuron is not a part of the network, because anything multiplied by zero will be zero. So actually you are removing these neurons from the network, right? So of course, if you have many weights which are close to zero, it is like removing a number of neurons and you might suffer from underfitting. Maybe this is also not desirable. Maybe a decision boundary like this seems an appropriate fitting where you can afford some errors in the training data, but this model is likely to generalize well when you apply it on the unseen data, right? So this was a general introduction to what regularization is and how it works, right? But how actually we implement it, there are different ways, right? So as I told you, we'll be discussing for L1, L2 regularization, dropout, data augmentation, and early stopping, right? So since we already had quite some technical discussion today, so I'll be skipping this one. We'll do it in the next week, and I'll just be directly going to dropout, right? So let me just go to dropout quickly, and we'll cover these later on. Yeah. Okay, so dropout, as you must have noticed in some of the pieces of code that I showed you, where I intentionally had to strike it off because we had not seen it. So it is a very common regularization technique. And what we do is that when we are training the model, we temporarily drop a neuron from the model, right? And when I say drop, what does it mean? It simply means that all the input and output connections to that neuron are disabled. In other words, there will be no update of weights for this neuron in that particular iteration, right? Now, how do we control what to drop, how much to drop? There's a parameter which is called dropout rate, which is normally less than 0.5, right? So if it is zero point 0.2, it means 20% probability. If it is zero point 0.2, it means every neuron has 20% chance of being dropped, right? So just to give you an idea, that on the left, maybe you have a model where you don't have any dropout, and you apply dropout to each layer separately with a and you specify the dropout rate. For example, this is the first layer, and you can say, okay, the dropout rate is zero point 0.5, which is 50%. For this layer, the dropout rate is zero point 0.5, and for this layer, there is no dropout, right? So when I say zero point 0.5, it means roughly 50% of neurons in this layer would be eliminated in that particular iteration, right? So for example, in one training iteration, I randomly say, okay, this neuron is dropped. Okay, so it means all the connections are gone. Similarly, in this layer, I have 4 neurons. So since I'm using a dropout rate of 50%, so 50% of 4 is 2. So any 2 random neurons will be disabled, means the connections, the input and output connections are gone. When you do the next iteration of backpropagation, it is very much possible that maybe there are 2 other neurons which are disabled because you are doing it randomly. Okay. Now let me just explain why it works and why dropping this, because when you look at this idea for the first time, it does not seem a smart idea to actually throw away your neurons, right? But let's see how it is helping to prevent overfitting, right? For that, there's a very good example in the literature that suppose you are running a small company of 3 people, right? Maybe you are looking after the finances, then this person is looking after the marketing, and this is actually product development. Okay, so just you have these 3 guys, the main people who are running this small company, right? Okay, so suppose this is you. You say, okay, every morning I will toss a coin, right? If it's a head, I will go to work, and if it's a tails, I will just stay home. Okay. So it means there's a 50% probability that you will go to work on every day, right? Because you are tossing a coin. So suppose on a good day you toss a coin and it says you stay home. Okay. So it means you don't come to the office and you have only these 2 in the office, right? Now, when you have only these 2, on a given day, say day 1, and there is some matter related to finance, since you are not available, so they will try to sort it out on their own, right? Maybe they are not very good in managing finances, but since they don't have any option, you are absent, so they will try their best to do something, right? And maybe over a period of time, they will also develop some sort of skills in management of finances, right? So it means they are not too much dependent on you. And now assume that not only you are tossing coin, but every one of these is actually doing the same thing. So maybe it is possible that on D2, the person who is looking after product development, he's not there. So in other words, you and the person who is responsible for marketing, they will have to take up his job. So initially, they would perform very poorly, but after some time, they will actually develop some limited skills in that particular domain that they can actually do at least something rather than nothing. Okay, so this is the idea of dropout, that you see you are sometimes dropping this neuron, sometimes this one, sometimes this one. So you are making sure that your model is not too much dependent on a specific subset of neurons, which is the key idea of, you can say, overfitting, right? That even if you throw away some neurons, your model is still able to perform better. So that's why your model generalizes better, right? And from the perspective of implementation, dropout is applied layer by layer, that you choose a layer on which you apply dropout. If you are dealing with CNN, then of course you will not apply dropout to convolutional layers because they are just learning features. You apply dropout only to the fully connected layers, right? Because in fully connected layers, you have more chances of overfit. Similarly, dropout is only at the training time, right? Because in every training iteration, you are dropping some random set of neurons. When the model is trained, then of course there is no dropout, right? At the test time, you will feed your data to the complete model without dropping anything, right? So all the you can say details which I shared with you, I have listed them in the slides as well, so that when you go through them in the revision phase, you actually can see this, right? So this is a visual illustration of dropout that you see. Now we don't have any dropout in this layer or this layer. We have dropout only in this, you can say, second last layer. Dropout rate is zero point 0.5, which is 50%, right? So you can see in every training iteration, there are total 4 neurons. 50% of 4 is 2 neurons. So randomly, 2 of the neurons will be dropped. They can be any 2 neurons, right? You can think of many combinations, right? So you see, this is visually illustrating you how dropout works. And as I told you, you apply it only to the fully connected layers, and dropout is applied only at the training time, not at the test time. Okay, and you just add dropout with the parameter value of p, and you can add it to your network. Now you can go back to the slides which I showed you earlier, and now that dropout layer will make sense to you. Okay, next, the second technique that I will share with you for today is data augmentation, right? Again, this is very common and very easy to understand, that a major cause of overfitting is that you have limited training data, right? So your model actually learns by heart that how to get a very good performance on that limited data, right? So if you can somehow enhance the size of training data, then it is likely that your model will not suffer from overfitting, right? And if you are dealing with images, of course, there are how you increase size of training data. It depends on what type of data you are dealing with, right? So in the perspective of CNN, since we are dealing with images, so you can actually apply different transformations on the images. They will represent the same class, but you can augment or increase the number of images, right? Now, even if you're not seen or taken a course on images, I'll just try to explain that why this works. That suppose you have an image of a cat, right? And you shift the entire image only by 1 pixel to the left or to the right, right? So if you see the two images to a human, they would not be able to tell any difference, right? Because shifting by 1 pixel does not actually is not noticeable by human eye. But for a computer, it is totally a different matrix, right? Because everything is shifted by 1 pixel. So whatever was in the first column of the matrix is now in the second column, and same goes for rows. So it is now a different training example with the same label, right? So you see, this way you can actually generate many copies of data by applying different transformations on the image, right? Because if you see it from the perspective of a machine, it is just a matrix of numbers. And if you slightly change these numbers, maybe say add 5 to every value, so visually it will be more or less the same image, but it will be a totally different matrix for the machine, right? So common transformations you can apply. Maybe you can flip the image. So you see we have one image, we flip it, it is still a cat, right? Similarly, you can pick random crops at different scales from the image. But of course, you have to be careful that when you pick a crop, it should actually look like a cat, right? For example, if someone just picks this part, you see, you cannot tell it's coming from a cat, and the label is cat, so it is a bit unfair that you expect the model to learn, you can say, from this small patch, right? Similarly, you can apply some contrast changes to the image, or you can translate the image, you can rotate the image, you can apply any transformation. So you see, from one single image, you can generate many images, right? So as I told you, you can even have a combination of different transformation, right? That you translate and rotate at the same time. So this is basically maybe some transformations applied to an image, right? So from a single image, we have generated 9 different images, right? So I'll quickly show you how to actually do that. So you see, suppose we have this image of dog, we load it in the memory with the imread function, and just we display it to the user using imshow. If we want to make copies, or you can apply different transformations, then you can do that using image data generator in the cloud, in the TensorFlow or Keras, right? So what you do is that, you see, this is important. What transformations you want to apply? Maybe we want to rotate the image. So this is the range, right, from -40 to 40. You want to shift it horizontally or vertically. So this 0.2 means 20% shift. Means sometimes randomly you will shift it in this direction or this direction, right? You can zoom the image up to 20%. You can apply maybe a horizontal flip, right? And using this transformation, you can actually generate multiple images. So what will happen is that your program, when it is running, it will randomly pick a combination of these transformations, right? For example, it can choose that I will rotate it by 20 degrees, I will zoom it by 10%, but I will not apply these two transformations. So you will get one image. Then it will again pick a random combination of these transformation that I will not rotate it. I will shift it 10% horizontally and 10% vertically, and I will not zoom it. Okay, so you see, by randomly picking, you can say a combination of these transformations, you can generate as many images as you like. Of course, in some cases, you see, it will give some artificial effects to the image, because when you are applying a transformation, there are some parts of the image which will have missing parts. You will have to fill those parts using some region filling algorithm, which may not be very perfect. So at times the images visually can look artificial, right? But you see, if you see it, you can still recognize it as a dog, right? So we expect the machine to do that as well, right? So for this example, I have written a small piece of code which is actually generating different copies of data and saving it on the disk. So, but you see, it is not a very smart idea, because if I have a data set, I am saving copies of images to disk, then I will need a lot of space, because I will have multiple copies of the same data, right? So better way is that you can directly pass the copies of data to the training algorithm, that rather than saving them on the disk, you only have the original copy of data on your disk, and then you simply apply a transformation and feed those transformed image to the learning algorithm. There's no need to save those transformations. This is the point, right? So there's also a way to do that, right? That, you see, when you are training a model, we normally use model.fit, right? With data augmentation, you'll be using model.fit generator, right? And the important size parameter here is that, you see, when you are training, you have a batch size. Okay, so our batch size is 128. So what will happen is that from your data set, it will pick a collection of 128 images. And then it will apply a random combination of transformations, whatever you have given in the constructor, right? So it will generate So from 128 images, it will generate 128 transformed images, and it will run one iteration of backpropagation. Then it will pick another set of 128 images, apply some random transformation, and feed them. Once your complete data set is exhausted, one epoch is complete. When you go to the second epoch, and it will pick the first set of 128, now it will apply some other random transformations. So you see, your algorithm is actually looking at the same data in every epoch, but since the combination of transformations is random, so in every epoch, it will see a differently transformed data, which is a smart way, right? That rather than showing exactly same set of images in every epoch, you randomly apply some transformation in first epoch, then some other random transformation in the second, third, and so on. So actually, in every epoch, you are showing your algorithm with different transform versions of the same data, right? So it is again a common technique that we commonly use when training CNN, or you can say any other model where we have limited data, right? So the last, you can say, strategy for today is early stopping, right? Now, what is early stopping? It is basically a type of cross validation, as it was being discussed in one of the queries. So what we do is that when you have some training data and the test data, in addition to that, you keep a small part which is called validation data. Okay, validation is different from the test data. So what you do is that when you are, suppose on this axis you have epoch. So when you are training your model, you train your model, your training loss is going down. But after every epoch, you also see the performance of your model on the validation data. Okay, so this is on validation data. So if it is going down, 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 then it is possible that at some point in time, the training error is going down, but the validation error starts to increase, or it becomes stable or something like that. This could be a signal that your model is might be suffering from overfitting, right? So how do we implement it? That we actually define a patience level. This 5 means that you will check validation error, and if there is no improvement for 5 epochs, right, means you will wait for 5 epochs, so you will not take an instant decision. If there is no improvement in validation error for 5 epochs, then you can prematurely terminate your learning, right? Maybe you had given 1000 epochs, but when you see that for 5 consecutive epochs there is no improvement, then training loss is going down, but the validation loss is not improving, or it is going up. It is an indication of overfitting, so I should stop here, right? So with that, I will also stop for today. So if you have some comments or queries, we can discuss those. Thank you.